Hello friends, I welcome you to lesson 3 of electric fields, and today I want us to look at the electric field due to a point charge. That's what we shall concentrate on. We shall concentrate at today. Earlier on in the previous syllabus, electric fields due to a point charge or electric field due to a point charge was now in A level. The previous concepts of electric field due to a uniform field was in AS that we have been looking at. So let's now move to more complex concepts of electric fields, and this will be electric fields due to a point charge or a spherical charge rather than parallel plates. Note that for parallel plates the field was uniform, and here we are going to see that the field can no longer be considered uniform if we have a point charge. So let's begin with let's straight away look at the electric field due to a point charge. I want you to recall that we could represent a point charge like that, or a spherical charge. Now, however big the sphere could be, a spherical charge could be considered a point charge for one major reason, and that is the field lines are actually radial. You will realize that when you look at the spherical charge, the field lines are radial, just like those that we saw in gravitation. Here I'm considering a spherical point charge. So the field lines appear as if they are coming from the center. And because the field lines are radial, if you were to extrapolate them backwards, they would appear to be meeting at the center, and they would appear to be originating from the center for a point positive charge. Therefore, it would give an impression as if the total charge of the sphere is originating from the center. But if the sphere is a conductor, we know that charge in a conductor resides just on the surface, and it distributes itself equally or evenly around the surface. Charge on a conductor resides just on the surface, and it distributes itself equally around the surface. If this was a positively charged sphere, the correct way of drawing the charges would be drawing the charged particles just on the surface of the sphere. But because the field lines are radial, as we have seen, they appear as if they are coming from the center of the charge. That's why we normally just put one positive sign at the center. So the sphere will be behaving as if it is a point charge, because for observations taken from outside the sphere, somebody gets an impression that the lines are appearing to radiate from the center. And if they are appearing to radiate from the center, we get an impression that the charge is concentrated at the center. In other words, we get an impression that for any point outside the spherical conductor, the charge on the sphere could be considered to act as a point charge which is placed at the center. But the truth is, if the sphere is a conductor, we are going to note that for any conductor, charge resides just on the surface of the conductor, and the charge distributes itself evenly or equally around the surface of the conductor. So that means essentially inside the conductor there is actually no charge. It is just on the surface. And therefore we shall later on see that there is no field strength inside the sphere. There is no field inside the sphere. There is no field inside the sphere. So we can say E inside the sphere, we should remember E is the electric field strength. E inside the sphere is going to be 0. So we are saying that a spherical charge can be considered to be a point charge. Reason: 1, the field lines are radial and they appear to be originating from the center. The field lines are radial and they appear to be originating from the center. Therefore, for observations from outside, it appears as if the field lines are originating from a point at the center. That's why a spherical charge may be considered to be a point charge. Okay, suppose now we have two charges. This could now take us to the concept of the force between point charges. The force between point charges. This force between 2 point charges is going to be given by what we call Coulomb's law. Before we go into the details of Coulomb's law, I want you to recall the following. Number one, we know from IGCSE and other concepts of physics that the law of charges states that like charges repel and unlike charges attract. Earlier on, we saw this when we were introducing electric fields. Like charges repel, unlike charges attract. But this law, unfortunately, does not tell us anything about the magnitude of the force with which they either repel or with which they attract. So that is a limitation. The law of charges tells us simply that like charges repel, unlike charges attract. But by what magnitude of force do they repel each other, or by what magnitude of force do they attract each other? That is a very important point. The magnitude of the force with which they either attract or repel each other was established by a French scientist called Charles Auguste de Coulomb. I think this is read as Augusta in French, although in English I think this would be Augustine. Charles Auguste de Coulomb was the first person to investigate the force between 2 point charges. And according to Coulomb, according to him, the force between any 2 point charges was directly proportional to the magnitude of the product of the charges and inversely proportional to the square of the distance between them, or to the square of the separation between the charges. This is a statement that we normally call Coulomb's law. The force between the 2 point charges, is directly proportional to the product of the charges. Let's call the one charge Q1, another charge Q2. And at the same time, the force was inversely proportional to the square of the separation between the two charges. This was following the inverse square law. So from this statement of Coulomb's law, we can now investigate the force between any 2 point charges. Note that I'm considering point charges, although if it is a single charge which is spherical, it is considered to be a point charge because the field lines are radial and appear to originate from the center of the charge. If we have two charges, again, two charges will be considered point charges if this is charge A and I have charge B somewhere here. Let's say both charges are positive. Also, these two charges, however big they could be, or if these are spherical charges, however big they could be, they would be still considered point charges if and only if their separation r is much greater than the dimensions of any of the charges. When I say dimensions, it could be the diameter of the spherical charge, it could be the radius of the spherical charge. The separation of the charges is far, far greater, or is much greater. When I write these two of these, it means much greater. That is much greater than the dimensions. It is much greater than the dimensions of any of these two charges. So Coulomb's law is normally applicable to 2 point charges for us to be able to tell the magnitude of the force. Let's see Coulomb's law in details. So let's consider two electrically or electronically charged spheres whose separation or the distance between the centers is much larger than the dimensions of the bodies or the charges or the charged spheres. And if that is very true, that the separation is much larger, then the charged bodies at a much larger separation than the dimensions of the bodies are referred to as point charges or very tiny charges. They could be very large spheres in everyday life, but if the separation between the two spheres is much greater than the dimensions of either of the spheres, then the two spheres can be considered or referred to as point charges. So let's consider these two charges separated by a distance r from their centers. Then Coulomb's law is telling us that actually the force between the 2-point charges is directly proportional to the product of the charges and inversely proportional to the separation of the two charges. So what we are saying is very simple. We are saying that force F, the force with which say charge Q1 is repelled by charge Q2, that force is directly proportional to Q1 times Q2. At the same time, that force is inversely proportional to the square of the separation between the two charges. When we combine these two, simply we can say force is both directly proportional to Q1, Q2 over R squared. Our task now is to remove the proportionality sign. That means the force F is going to be equal to a constant we shall call K times Q1, Q2 divided by R squared. So by Newton's third law, the force which Q1 experiences from Q2 must be equal but opposite to the force which Q2 experiences from Q1. The constant K is a constant of proportionality that we are going to establish later on. So the law is only going to be appropriate or applied to point charges or cases where the separation is much larger. If the separation is much larger still, these can be considered to be point charges. So we are saying K is a constant, and this constant we are yet to establish it. K is a constant of proportionality which we are going to establish. However, I am saying that we shall always be calculating the force between 2-point charges from this expression here. So let us see what is K, or how do we come up with K. To understand K, we need to first establish what we call the permittivity of a medium. Permittivity of a medium. So the force between two charges does not only depend on the separation. Yes, it depends on what separate it depends on the separation between the two charges, but also depends on what is between the two charges or what actually separates them. Is it an insulating material or it's a vacuum? So we are saying that the force between two charges is also depending on what separates them. What is between the two charges? Are they placed in a liquid? Is there an insulating material between them, or they are placed, or there is a vacuum between them, or they are placed in a vacuum? So experiments by Coulomb established that actually the constant K, which was the constant of proportionality, was given by 1 over 4 pi epsilon m. This is read as epsilon, and epsilon m is called the permittivity of a medium in which the charges are placed. The permittivity of the medium, of course, depends on the nature of the medium itself. So the constant of proportionality K that we have already arrived at earlier on is depending on the permittivity of the medium, which is actually a characteristic of the medium itself. It depends on what is actually between the charges. What is the nature of the substance between the charges? If between the charges we have a vacuum, or the charges are placed in a vacuum or free space, then we replace epsilon m with epsilon naught. We replace epsilon m with epsilon naught, and epsilon naught is called the permittivity of free space, which is given a value of 8.85 times 10 power negative 12 Coulomb squared per Newton per meter squared. This constant is normally given in the list of formula in an exam, and this quantity is called the permittivity of free space. That quantity is called the permittivity of free space. Therefore, the quantity K, the quantity K, therefore the quantity K, sorry, this is the quantity epsilon, naught, sorry, I need to correct this. So the quantity K is going to be quoted. Let's try to quote quantity K correctly. The quantity K is going to be equal to 1 over 4 pi epsilon naught, which will be 1 over 4 pi times, this will be 8.85 times 10 power negative 12. And when we press our calculator, the quantity K will always be quoted as 8.99 times 10 power 9. This will be newtons meters squared per Coulomb squared. When you divide this, the units are going to be inverted. So it becomes newtons meters squared per Coulomb squared. So the quantity K can always be quoted as 8.99 times 10 power 9 newtons per meter squared. Newtons meters squared per Coulomb. In every calculation, we can always quote that quantity as the quantity of proportionality, 8.99 times 10 power 9. You can press your calculator to verify that quantity. It's 8.99. It's not 8.885. This is epsilon naught. It's 8.99 times 10 power 9 newtons meters squared per Coulomb. So that is the quantity K. So in our calculations, we can always use that quantity so that it gives us or it helps us to find the value of the force between 2-point charges. Of course, you must have noted the following if you have studied gravitation. You must have noted a few important points. Number one, you must have tried to compare the constant that you have just established and the constant in gravitation. Remember, we saw that capital G was 6.67 times 10 power negative 11 in gravitation. This was, I think, newtons meters squared per kilogram. Now we have established K as 8.99 times 10 power 9 newtons. Actually, this is Newton meters, not per meter. Newton meters squared. This was per kilogram squared. So this is Newton meters squared per Coulomb squared. You notice that these units only deviate in the last quantity per kilogram because it was due to the mass. This is per Coulomb because it was due to charges. So in comparing the magnitudes, you are going to first of all notice that actually the magnitude of K is of about 20 orders larger than the magnitude of G. Because when I divide 10 power 9 by 10 power negative 11, I'll get 10 power 20. So it means the K is of about 10 power 20 orders. It is of 20 orders of magnitude larger than G. What is the implication of that? It means that if we consider two charged particles placed at a certain distance r apart, the force due to their charges, which we are going to call the force due to the electric field, is going to be much greater than the force due to the gravitational field or due to their masses. Many times in calculations, the force due to their masses is going to be ignored because the force due to the electric field is much larger than the force due to uh, the gravitational field. Also note that their units only deviate in the last quantity. The other one for gravitation, because it deals with the masses, it was per kilogram squared. And here we are dealing with the charges, it is per Coulomb squared. So you must have noticed, especially you have compared the units, and also you have compared the magnitudes. We have compared the magnitudes. We have also compared the magnitudes, and we have noticed we have seen the consequence of the difference. We have seen that K is 20 orders, that is 10 power 20, greater than, or it's about 10 power 20 times greater than the gravitational field constant. And we saw that the implication of this is that the force due to the electric field or the force due to the charges is much larger than the force due to the masses. Therefore, we are coming to a conclusion. We are coming to a conclusion that actually the force between two charges placed in a vacuum could be given by Q1, Q2 over 4 pi epsilon naught. But remember, 1 over 4 pi epsilon naught was 8.99 times 10 power 9. Therefore, the force could be given as 8.99 times 10 power 9 multiplied by Q1, Q2 over R squared. Suppose the charges are not placed in a vacuum or they are placed in another medium. Then it means we retain our epsilon m, which was permittivity of the medium. So if the charges are not placed in a vacuum, then epsilon naught is replaced with epsilon m. And this should be taken care of when we are doing our calculations. It should be taken care of when we are doing our calculations. Okay, let's also see, sometimes we are given the relative permittivity of a medium rather than its actual permittivity. Suppose we are given the relative permittivity of a medium. What do we mean by relative permittivity? Relative permittivity is simply the ratio of the permittivity in a given medium compared to the permittivity of free space. So the ratio of permittivity of any medium, remember permittivity of any medium is given as epsilon m, compared to the permittivity of free space, which is given as epsilon naught. The ratio of the two is going to be called the relative permittivity of the medium. In other words, relative permittivity of a medium is going to be the permittivity of a material or a medium divided by the permittivity of free space. This is normally written as epsilon r to mean relative permittivity. So in symbols, we shall say epsilon r can be the same as epsilon m over epsilon naught. So it implies that when given epsilon r, then permittivity of a medium can be quoted as epsilon r times epsilon naught. The relative permittivity of free space, I think it is about 1.00. The relative permittivity of air is around 1.0006. That's why we say when the charges are put in free space or in a vacuum, epsilon m is the same as epsilon naught because the relative permittivity is approximately 1. Epsilon m, that is permittivity of the medium, is quoted as epsilon naught because the relative permittivity is 1.0. Remember, we have established that epsilon naught is a constant which is normally given, permittivity of free space, that is 8.85 times 10 power negative 12, which is always given. So at this point, there are a few things you must have noted. Number one, you must have noticed that in both Coulomb's law and Newton's law of gravitation, the forces or the force varies inversely proportional to a property of each object. Note that Newton's law was telling us that the force was directly proportional to m1, m2, and inversely proportional to the square. That was Newton's law of gravity. We are now seeing that for Coulomb's law, this was Fg. For Coulomb's law, the force to the electric field is also directly proportional to Q1, Q2, and inversely proportional. By the way, this is R squared. That is the separation squared. So that was Newton's law compared to Coulomb's law. So in both cases, the force varies as the inverse square of the separation. Force varies as the inverse square of separation. These forces can act even when the two objects are not touching. Therefore, we call them what? Non-contact forces. They do not need contact. So we say they can act at an infinite range. Gravity acts at an infinite range. Electric fields or the electromagnetic force also can act at an infinite range. But there is one major difference that you have also noticed. Now, this is we did not have negative masses. Therefore, you must have noticed that in gravity, the force was always attractive. In gravity, the force was always attractive because we do not have negative masses. But in electric fields, we are going to realize since we have both positive and negative charges, the force could either be attractive or repulsive, depending on the charges. Since we have both positive and negative charges, in electric fields, the force can be attractive or even repulsive. So when we are doing calculations, we shall always have that in mind, that the force can either be attractive or it can be repulsive. Let us see an example. Let's see an example. Example. Find the force between 2-point charges, positive 4 microcoulombs and negative 3 microcoulombs, placed at a distance of 10 centimeters apart in air. Find the force between 2-point charges, positive 4 microcoulombs and negative 3 microcoulombs, placed at the distance of 10 centimeters apart. Remember, the force is directly proportional to the product, so it is equal to a constant times Q1 times Q2 divided by the square of the separation. But also remember that K is equal to 1 over 4 pi epsilon m, where epsilon m is the permittivity of the medium. Now that it is placed in air, this will be 1 over 4 pi epsilon naught. Remember, epsilon naught is 8.85 times 10 power negative 12. So when you substitute it here, this gives you 8.99 times 10 power 9. So I'll just be, whenever they are placed in air or in a vacuum, I'll just be using 8.99 times 10 power 9 as the constant. So the force here, F, will be equal to 8.99 times 10 power 9 multiplied by the product of the charges, which will be 4 times 10 power negative 6, then times the 3 times 10 power negative 6, divided by the separation of the charges, which is 0.1 squared. I've converted 10 centimeters to meters. Because they are unlike charges, this is positive, this is negative, the force here will simply be attractive. By convention, by the way, attractive forces are positive, are negative. Sorry, Yes, attractive forces are negative by convention, and repulsive forces are positive. That's why in gravitation we saw that the gravitational field strength would always be considered negative because the force was always attractive. Okay, so this same force is exerted by the 4 microcoulomb charge onto the other one, but the two forces given by Newton's third law will be equal but opposite. The 4 microcoulombs exerts this force, which my calculator is giving me as 10.79 newtons. So the 4 microcoulomb charge exerts this force on the 3 microcoulomb charge. The 3 microcoulomb charge also exerts the same force on the 4 microcoulomb charge, but these two forces are equal but opposite. In other words, if this is positive 4 microcoulombs somewhere here, and this is negative 3 microcoulombs somewhere here, this is being attracted by this charge in that direction with this force. And this is also being attracted by this charge with that same force in opposite directions. Example number 2. We have three charges this time placed on a straight line. Find the resultant force on the charge at B. We want the resultant force on the charge at B. So if we consider the charge at B, it is positive. So what is the effect of charge A on charge B? You will realize A is negative, B is positive. It means A is attracting B in that direction with a force which is directly proportional to the product of the charges, but inversely proportional to the square of the separation. That's number one. Number two, let's now consider charge C. C is negative, yet B is positive. C is also going to attract B in that direction. So there are two forces, F1 and F2, which are acting in opposite directions. The resultant of the two forces is the resultant force at B. Because this is nearer, the distance is smaller, of course, your common sense will tell you that this is actually greater than the other one. The resultant force is obtained by vector methods or by vector addition because the forces are vectors. So let's first find F1 maybe. F1, remember the force is going to be K Q1 Q2 over R squared. We are assuming they're in a vacuum. So F1, which is to the left, is going to be 8.99 times 10 power 9, then times the product of the charges 3 times 10 power negative 6 times 4 times 10 power negative 6 divided by the square of the separation, which is 0.1 squared. This would give you, of course, we have done something similar to this, 10.79 newtons. This is attracted, so B is attracted towards A, so that will be to the left. I will say to the left. In other words, B experiences this force to the left. If I consider the charge C, I will call this F2. The force experienced by B caused by C is to the right. And this will also be 8.99 times 10 power 9 times the product of the charges 4 times 10 power negative 6 times 7 times 10 power negative 6 divided by the square of the separation, which is 0.05 squared. And of course, this is half of the other one. So this is going to give me, pressing the calculator, so this is giving me 100.69 newtons, and this is to the right. Because force is a vector quantity and they're in a straight line, then it means the resultant force on charge B is going to be equal to 100.69 minus 10.79. This gives us So this is giving me 89.9 newtons. And this is going to be to the right or towards C. This will be to the right or towards C. So that is the resultant force on charge B. Note that in calculation we're not including the negative and the positive signs. The negative and positive signs are just guiding us to tell the direction of the force on the charge. They are guiding us to tell the direction of the force on the charge. Let us also see the force. Find the resultant force on charge A. I'll only find on charge A, and you should be able to find on charge C. I will use the same space for the resultant force on charge A so that you'll be able to find the resultant force on charge C. Let me clear this. So we are now finding the resultant force on charge A here. So if I consider B, B is positive, A is negative, it means B is pulling A. So A experiences a force to the right caused by B. I'll call this one F1. If I consider C, C is negative, yet A is also negative. It means C is repelling A. So A is repelled by C to the left. So I'll call this one F2. So if I find F1, remember F is equal to K Q1 Q2 over R squared. So F1 is going to be K, which is 8.99. We are assuming they're in a vacuum, times 10 power power 9. Then multiplied by the product of the charges, which is 3 times 10 power negative 6 times 4 times 10 power negative 6. This is divided by the square of the separation, which is 0.1 squared. This has given us 10.79 newtons, but this is now to the right. This is to the right. Similarly, we can consider F2. F2 is going to be equal to 8.99 times 10 power 9 times the product of the charges, which will be 3 times 10 power negative 6 times 7 times 10 power negative 6, which is divided by the separation of the charges, which is 10 plus 5, that is 15. So it becomes 0.15 squared. Then we press our calculator. Okay, so my calculator is giving me 8.39 newtons, and this is to the left. So it means the force to the right is greater than the force to the left. It even makes sense because the force to the left is due to a charge which is just 10 centimeters from A, and the force is also dependent on the distance. Remember, it decreases as the square of the distance. So the resultant force on A, I'll quote FA, is going to be 10.79 newtons minus 8.39. So this gives us 2.4 newtons to the right, or towards C, as simple as that. So as an assignment, you should be able to find the resultant force on the charge C, which is of negative 7 microcoulombs. Okay, example number 3. Example number 3. We have 3 charges still placed on a straight line, Q1, Q2, and Q3. Find the resultant force on Q2. Resultant force on Q2. So still this is positive, the other one is negative, this is negative. So what happens to Q2 if I consider Q1? Because Q1 is positive, Q2 is attracted, so it experiences a force to the left. I'll call this one F1. If I consider Q3, Q3 is negative, yet Q2 is negative, so Q3 repels Q1. So Q2 experiences another force caused by Q1. I'll call it F2, which is still to the left. So it means the resultant must be, of course, to the left. Remember, the force F is equal to K Q1 Q2 over R squared. So the resultant force will just be the sum of these two. I'll just press the calculator at once. So the resultant force F on Q2 is going to be that due to Q1, which is F1, that is 8.99 times 10 power 9 times the product of the forces, the charges, which is 2 times 10 power negative 6 times 3 times 10 power negative 6, divide by the separation of the charges, which is 0.2, 0.02. So this is 0.02 squared. That is the separation of the two charges, plus the second force is in the same direction, so I just add 8.99 times 10 power 9 times product of the charges, which would be 3 times 10 power negative 6, then times 4 times 10 power negative 6, divided by the separation of the charges is 0.04 squared. We press the calculator. So I am getting 134.85 newtons plus 67.43 newtons. You can check. And when I add, I get 203.28 newtons. And this is towards Q1, or towards the left. 203.28 newtons to the left. As an assignment, you should be able to find the resultant force on Q1 and also find the resultant force on Q3, just following the same procedure. Remember, when I consider Q1, Q2 is attracting it to the left, to the right, because this is positive, the other one is negative. Q3 is also attracting it to the left because this is positive, the other one is negative. So the resultant force is going to be F1 and F2 to the right. If I consider Q3, Q2 will repel it to the right, yet Q1 will attract it to the left. So the resultant force will be the difference between these two values. As an assignment, you should be able to calculate Q1 and Q3. Further examples, number 5. 2-point charges. I deliberately skipped question 4 because it was almost the same. So I decided to skip it. Question 5. 2-point charges, 5 microcoulombs, and 2 microcoulombs are placed in a liquid of relative permittivity 9 at a distance of 5 centimeters apart. Have it in mind that relative permittivity epsilon r is the same as epsilon m over epsilon naught. If relative permittivity is 9, so it means 9 times epsilon naught is equal to epsilon m. So we want to find the force between the two charges. The force is equal to a constant, or this will be Q1 times Q2 over 4 pi epsilon m times r squared. But remember, epsilon m is 9 times epsilon naught, so this will be equal to Q1 times Q2 over 4 pi times epsilon naught, then times 9 r squared, because this is 9 epsilon naught, so I maintain epsilon naught, then I pull away the 9. Why am I doing that? Is because I know that 1 over 4 pi epsilon naught is 8.99. So this will be 8.99 times 10 power 9. Then multiply by the product of the charges, 5 times 10 power negative 6 times 2 times 10 power negative 6, divide by the separate, this will be 9 times r, 5 centimeters, that will be 0.05 squared. And this, when you press your calculator, it gives you the force between the two charges. Note how we dealt with the relative permittivity here. So this is giving me, from my calculator, it is giving me 4.0 newtons. You can verify. So if the permittivity of the medium or relative permittivity are not given, we are always going to assume that the charges are in air or in a vacuum. They are in air or a vacuum. If the permittivity of the medium is not given, or the relative permittivity of the medium is not given, we are always going to assume that the charges are in air. If they are not in air, then the permittivity of the medium or the relative permittivity of the medium will be given. Example 6, two insulated metallic spheres, A and B, have their centers separated by a distance of 60 centimeters in air. Calculate the force of electrostatic repulsion between them if a charge of 5 times 10 power negative 80 coulombs, if a charge on each sphere is 5 times 10 power negative 8 coulombs. Let's try to find the force or the electrostatic force of repulsion. But of course we know that, so this was number 5. Number 6, we know that the force is equal to the product of the charges, which is going to be 8.99 times 10 power 9 times the product of the charges, which will be 5 times 10 power negative 8. I will just square this because the charges on each sphere is, the charge on each sphere is that. Divide by the square of the separation. They are 60 centimeters apart in air, so this will be 0.6 squared. And we press our calculator. So pressing the calculator, I'm getting 6.24 times 10 power negative 5. 6.24 times 10 power negative 5 newtons as the force between the two charges. Okay, next, example number 7. What is the force of repulsion if the charge on each sphere above, that is in question 6, is doubled? I think that is an obvious question. If the charge is doubled, initially the charge was 5.0 times 10 power negative 8 coulombs. If it is doubled, we just multiply that by 2. And part B, the two spheres are placed in water whose dielectric is the same as relative permittivity. whose dielectric is 81. So in part A, we are doubling the charge. So the force is going to be K, which is 8.99 times 10 power 9 times the product of the charges will now be 10 times 10 power negative 8, and this will be squared because there are two charges and this has been doubled. Then divided by the square of the separation. They said the distance is halved. The distance, remember, was 60 centimeters initially. Initially, r was 60 centimeters. Now it is halved, so r is now 30. So this will be over 0.3 squared. Then we press our calculator. So pressing the calculator, I get 9.99 times 10 power negative 4 newtons. In part B, the two spheres are placed in water. Initially, we have considered them in a vacuum or in air. Now they are placed in water whose relative permittivity is 81. So remember, relative permittivity is the permittivity of the medium over the permittivity of free space, which means 81 is equal to epsilon m over epsilon naught, which means the permittivity of a medium is going to be 81 times epsilon naught. So we simply substitute force is equal to K, or we can say Q1, Q2 over 4 pi epsilon m times r squared, which is going to be Q1, Q2 over 4 pi, where there is epsilon m, I put 81 epsilon naught. So it becomes epsilon naught times 81 r squared. And 1 over 4 pi epsilon naught is K. So this becomes 8.99 times 10 power 9. Then times the product of the charges, assuming the magnitude has remained the same. So it will be 5 times 10 power negative 8. And this is squared because there are two charges, Q1 and Q2. Divide by, now here I've removed 1 over 4 pi epsilon naught. So I remain with 81 times r has remained the same, 60, so that will be 0.6 squared. So we press our calculator. So pressing the calculator is giving me 7.707 times 10 power negative 7 newtons. You notice that this becomes a smaller force compared to the other one. That is, when we include a dielectric, or when we remove a vacuum between the two charges, the force becomes weaker, or the force reduces. So the force is now 7.7 times 10 power negative 7 newtons. Okay, I think at this point we can now calculate the remaining questions. Self-check. Calculate the value of two equal charges if they repel each other with a force of 0.1 newtons when placed 50 centimeters apart in a vacuum. What would be the size of the charges if they were straightened in an insulating liquid whose permittivity was 10 times that of a vacuum? And then a test charge Q, positive 2 microcoulombs, is placed halfway between a charge Q, which is positive 6 microcoulombs, and a charge which is positive 4 microcoulombs. These are 10 centimeters apart. This one and this one are 10 centimeters apart. Find the force on the test charge and its direction. So in other words, you have, if you were to put this on a straight line, one side you put positive 6 microcoulombs, The other side you put positive 4 microcoulombs. These are 10 centimeters apart. And the test charge is placed somewhere between them, that is halfway. Here we have positive 2 microcoulombs. That means this is 5 centimeters, 5 centimeters. So you should be able to find the force on the positive 2. 3-point charges are placed at the following points on the x-axis. At 0 we have that, at 40 centimeters we have that, at 120 centimeters we have that. Find the force on the negative 3 microcoulomb charge. So if you consider a straight line, at 0 you have plus 2 microcoulombs. Then at 40, so that distance should be 40 centimeters, you have negative 3 microcoulombs. And at 120, of course from 0 to 120, it means this is 40, 120 minus 40, this would be 80, I think, 80 centimeters. This is negative 5 microcoulombs. So we want the force on this charge here. You should be able to find that. Calculate the force between two electrons, which are 1.0 times 10 power negative 10 meters apart. So remember the charge is 1.6 times 10 power negative 19 coulombs. In number 8, they said calculate the value of two equal charges. They are equal in magnitude if they repel each other with that force. So just to give people a hint, the force is 0.1. But the force is the product of the charges. Since they are equal, to be q times q, which becomes q squared, divided by, or times a constant k, divided by r squared, where r is the square of the separation. R has been given as 50. K is known if they're in a vacuum. K is 8.99 times 10 power 9. So by substituting, you should be able to find q if f is 0.1. And then now you should be able to replace. Instead of using a vacuum, they are now in a liquid whose permittivity is 10 times that in a vacuum. That is, permittivity of the medium is 10 times epsilon naught. So in the expression, we shall no longer use 8.99, but we shall replace epsilon naught with epsilon m, which is that. So the force is going to be q squared divided by 4 pi epsilon m times r squared, where epsilon m will be 10 times epsilon naught. You should be able to find q again. You should find q here and also find q there. I've given you a hint. So you must be able to accomplish, you should be able to accomplish that self-check. Let's look at the electric field strength, or E, due to a point charge. We have introduced a point charge, but we haven't yet talked about the electric field strength. We have just seen the electric field due to a point charge. But how about the strength? Electric field strength due to a point charge. Electric field strength due to a point charge. So let us consider a point charge to be spherical in nature. Earlier on, we have seen that if we have a point charge, let's say it is positive, the field lines are radial and appear to be originating from the center, so they radiate outwards. If the charge is negative, the field lines are radial and appear to be terminating to the center. So what does that mean? Remember, to define an electric field or electric field strength, we always imagine a unit positive charge placed in the region of the electric field. The direction in which the charge moves is the direction of the field. So the direction of E is actually radially outwards. In other words, If we imagine a positive charge placed somewhere in a region of the field created by a positive charge, this is a unit positive charge, that is a charge of positive 1 coulomb. We imagine a unit positive charge placed in the region of the electric field. If this is a positive charge placed at P, it will be repelled. That means the field at this point caused by this large charge is radially outwards. In other words, a positive charge gives rise to a repulsive force. Note that by convention, a repulsive force is always, or a repulsive field is considered to be positive. On the other hand, if we consider a negative charge creating the field, we imagine a unity positive charge, positive 1 coulomb placed at point P. This charge will automatically be attracted towards the negative charge. Therefore, a negative charge gives rise to an attractive field. So to define electric field strength, we must consider a unity positive charge placed in the region of an electric field. Now let's consider this to be small q. By definition, electric field strength is defined as force acting on a unit positive charge. But the force between two charges is given by, let's say the distance between the two charges is r. The force between the two charges is given by the product of the charges q, say q1 or capital Q times small q, divide by, of course there is a constant here, which constant if they're in a vacuum is 1 over 4 pi epsilon naught. I will just use, I want to use 4 pi. So this is 4 pi epsilon naught. Then times the square of the separation. So if I substitute this into that expression, you realize that E is going to be the force, which is Q times small q, over 4 pi epsilon naught r squared divided by the small q in the denominator. So this cancels with that q cancels. So E is therefore going to be Q divided by 4 pi epsilon naught r squared. So the electric field strength due to a point charge is going to be given by that expression there. We imagine a unit positive charge placed in the region of the electric field or in the electric field. The force it experiences and the direction it experiences is actually the electric field strength at that point. The direction in which a unit positive charge moves is actually the same as the direction of the field. The direction in which a unit positive charge will move is the direction of the electric field. The force it experiences at that point is the electric field strength. Therefore, we are saying that E due to a point charge is given by this expression here. And epsilon naught is still the permittivity of free space. Epsilon naught is the permittivity of free space. It is the permittivity of free space, which is 8.85 times 10 power negative 12, which when we divide 1 over 4 pi epsilon naught, we get 8.99 times 10 power 9. If the charges are not in a vacuum, then epsilon m is replaced by epsilon naught is replaced by epsilon m, where epsilon m is the permittivity of the medium in which the charges are now placed. I want you to realize that electric field strength, just like a gravitational field strength, is a vector quantity. So the resultant can be obtained by vector methods. Before we advance, you try to compare this electric field strength being equal to Q divided by 4 pi epsilon naught times r squared, compare with the gravitational field strength G that we obtained that was equal to capital G times capital M over r squared. You notice that in both cases, the field strengths are inversely proportional to the square of the separation. The field strengths, I'm talking about strengths because I'm considering two here. One is an electric field and another one is a gravitational field. In both cases, the field strengths are inversely proportional to the square of the separation. In other words, the field strengths follow the inverse square law. The inverse square law. So in going back to electric field strength and ignoring gravitational field strength, because we have already seen that in gravitation, we can come up with a graph of gravitational field strength, electric field strength against distance, maybe from the surface if we considered a spherical charge. I want you to always recall, inside the conductor, E is zero. Reason, I have earlier on mentioned that charge resides just on the surface. And if charge resides just on the surface, it means the electric field strength we can consider starts from the surface and decreases as you move away from the surface, because it follows the inverse square law. Inside the conductor, electric field strength will be zero. No charge resides inside. Charge resides just on the surface. Charge resides just on the surface. So if I was to sketch a graph, of electric field strength E with the distance, the graph will look like this. Where now this could be inside a sphere. If this was a sphere, let me draw here a sphere of radius. Let this be the radius of the sphere. Let's call this one R. So inside the conductor or inside the sphere, E is going to be 0. So the line will be along the x-axis. But as you move away from the sphere, of course, on the surface of the sphere, E is given as a constant k times q over 4 over r squared, where k is 8.99 times 10 power 9. So as you move away from the surface, E is a certain value on the surface. As you move away from the surface, E varies as the inverse square. The work done to move from the surface to a certain point, for example, is sometimes referred to as the potential, or V is going to be the work required to move from the surface to a certain point, or the change in potential energy, which we shall see later on as we advance. So from this graph, we notice something. The graph shows a classic inverse square law, and the area under the graph is actually the work done to move a unit charge from, say, the surface to a certain point x, or through a distance to a certain point x. The work done to move from the surface, to move the charge, a unit charge from the surface to a certain point, is given by the area under the graph. Note that I have mentioned E is a vector quantity. The resultant electric field strength is obtained by vector methods. The resultant electric field strength is obtained by vector methods, as we have seen we have seen with the force. Let's see a few examples. Number one, a 4 microcoulomb charge is 5 centimeters from point B. Find the electric field intensity E at point B. I have mentioned, to define electric field intensity or field strength, we imagine a unit positive charge at point B. A unit positive charge, that is a charge of 1 coulomb, positive 1 coulomb at point B. The force it experiences is actually the electric field strength. Therefore, in our solution for number 1, electric field strength is going to be K times Q over R squared. Remember, K is 8.99. I said if the relative permittivity or the permittivity of the media is not given, then we assume the charges are in a vacuum. So K is going to be 8.99 times 10 power 9, then times the charge creating the field 4 times 10 power negative 6, divided by the square of the separation 0.05 squared. We press our calculator at this point. So this is giving me 14.4 times 10 power 6 newtons per coulomb. Note that we imagine a unit positive charge at B. The force it experiences at that point is the electric field strength at that point. Number 2, if Q1 and Q2 equal to that, find the electric field strength E at P if Q2 is 2 centimeters from P. So let us assume we have two charges as given. Q1 is 4 microcoulombs. Q1 is 4 microcoulombs positive, and Q2 is negative 6 microcoulombs, but Q2 is 2 centimeters from P. So P is a point. This is 2 centimeters. And of course, if the distance between them is 5 centimeters, this will be 3 centimeters. So we want to find the electric field strength at point P. We imagine a unit positive charge at point P, a charge of 1 coulomb at point P, to find the electric field strength here. If we imagine a unit positive charge at P, when I consider the charge Q2, Q2 is going to attract it to the right because Q2 is positive. I mean, it is negative. It will attract our unit positive charge. Yet at the same time, Q1, which is positive, is going to repel it to the right. So it means the resultant force is on one side. It is towards Q2. So the resultant electric field should also be towards Q2. So that one I will just add. Remember, it is a vector quantity. Vector addition can apply here. So the electric field strength E at point P is going to be that caused by this one. Remember, E is KQ over R squared. I will just substitute. This will be 8.99 times 10 power 9. If I consider Q1, this will be 4 times 10 power negative 6 divided by the distance, which is 0.03 squared, plus, because they're in the same direction, I will just add. For this one to be 8.99 times 10 power 9 times, the charge is 6 times 10 power negative 6 divided by the square of the separation, which is 0.02 squared. Okay, so you can press the calculator and we find the electric field strength at point P. Note that in this case, I've considered P to be between Q1 and Q2. It's also possible for P to be on the other side. If that was the case, then I can try again to modify this. If P was on the other side, if P was on the left, so let's have a different scenario because the question is not very specific. So Q1, let's say it is there, Q2 is at that point, and we are saying P is on this side. Then in that case, the scenario could somehow change. Note that this is positive, this is negative. Positive 4 microcoulombs, and this is negative 6 microcoulombs. We imagine a unit positive charge placed at point P. So this could be positive 1 coulomb. A unit positive charge placed at point P. So you will realize that actually, if I consider Q2, Q2 attracts it to the left, and yet Q1 repels it to the right, because Q1 is positive, they repel. Q2 is negative, they attract. So Q1 repels it to the right, yet Q2 attracts it to the left. In this case now, I will subtract the values to find the resultant electric field strength. But remember, the distance now changes. If this is 5 centimeters and this is 2 centimeters, the distance for P from Q1 is going to be 7 centimeters. So let me call this one E1, I call this one E2. So for E1, E1 is due to 6 microcoulombs, so that will be 8.99 times 10 power 9, then times 6 times 10 power negative 6, divided by the square of the separation, which is 0.02 squared. That is to the left. If I find E2 caused by Q1, this will be, how did I alter this? Let's say Q2 causes E2, Q1 causes E1. So this is E2, let this be E1. So E1 will be 8.99 times 10 power 9 times 6, so times 4 times 10 power negative 6, divided by the distance is now 0.07 squared. This will give you the new value of E2, of E1. The resultant will be now I think E2 is greater than E1 because of the distance. So I will simply say E2 minus E1. The resultant electric field strength will be to the left because E2 is to the left. So you just subtract these two values and you get the answer. I'll just put in my calculator at once. So this was the first case when I considered P in between. You can press your calculator to find that answer. And the second case where P is on the other side, I'll just calculate one case. So when I subtract, I'm getting 1.2 times 10 power 8 newtons per coulomb. You can press the calculator and also find that. So the units of electric field strength will not change, they will remain the same. Example number 3. We have point B between A and C. Find the electric field strength at point B. Remember, we imagine a unit positive charge at point B. The force it experiences is the electric field strength at that point. So let's find the resultant force. I mean the resultant electric field at point B, or field strength at point B. A is positive, it repels it to the right. C is negative, it attracts it to the right. That means the resultant is on one side, it is to the right. So I will just add. So electric field strength is KQ over R squared. So the resultant electric field strength at point B will be that one caused by A, which is 8.99 times 10 power 9 times the charge, which is 5 times 10 power negative 6, divided by the square of the separation, which is 0.1 squared, plus that caused by C, because they're on one side, I'll just add. So that is 8.99 times 10 power 9 times 3 times 10 power negative 6, divided by 0.05 squared. You press the calculator. So by pressing the calculator, we are getting 15.3 times 10 power 6 newtons per coulomb. And this will be towards C, or to the right if you want, but that is towards towards C or to the right, because electric field strength is a vector quantity. One more last example so that you could be able to do the self-check. You should be able to do a self-check at this point. You should be able to do a self-check at this point. Find the electric field at a distance of 0.1 meter from a charge of 2 nanocoulombs. So E is going to be KQ over R squared. We imagine a unit positive charge at that distance. So this will be equal to 8.99 times 10 power 9 times the charge, which is 2 times nano is 10 power negative 9, divided by the square of the separation, which is 0.1 squared. So we press our calculator. So this is giving me 1,798. 1,798 newtons per coulomb. The way I'm writing this, it is appearing as if the units are smaller, yet this is supposed to be a capital letter C. Newtons per coulomb, newtons per coulomb. So that is the electric field strength at that distance. Note that if the relative permittivity or the permittivity of the medium is not given, we shall not use K as 8.99 times, we shall use K as 8.99 times 10 power 9. If permittivity of the medium is different from that of free space, or the relative permittivity is not given, is given, we shall not use 8.99. Remember to use E as Q over 4 pi epsilon m times R squared, where epsilon m is the permittivity of the medium. Always remember that. Unless it is a vacuum, that's when we use K as 8.99 times 10 power 9, or unless it is air. Another medium, this cannot work. Self-check. Self-check number 3. Calculate the electric field intensity created by a point charge of 1 microcoulomb at a point situated 2 meters in air and in water. So we have two questions in one. You first calculate in air, then you calculate in water, where the relative permittivity in water is 80. A charge of positive 6 microcoulombs experiences a force of 2 millis 10 power negative 3 in the positive x direction at a certain point in space. What is the electric field intensity, that is E, there before the charge was there? Describe the force a negative 2 microcoulomb charge would experience if it was used in place of a positive 6. So when we say describe, you'll have to find the magnitude and tell us the direction. Then, but remember this was okay. Remember, force is the product of the two charges over the square of the separation times the constant. Coulomb's law, the force is directly proportional to the product of the charges and inversely proportional to the square of the separation. 2-point charges Q1, Q2 are placed at the distance 5 centimeters apart, at which point on the line joining them is the electric field strength 0. That means there is a point on the line joining them where E becomes 0, but note that these are unlike charges. This point cannot be between them. So if this is Q1 and this is Q2, This point is either this side or the other side. It is either this side of Q2 or it is the other side of Q2. So when you are calculating, you must consider that. If the distance between them is 5 centimeters, then you can add x and put a point P where E is 0. Then you can now find E due to Q1 from P, E due to Q2 from P, and then you solve, you find x. In a simplified mode of a hydrogen atom, the electron is at a distance 5.3 times 10 power negative 11 meters from the proton. The proton charge is that, capture the electric field strength of the proton at this distance. So if the electron charge is that, the proton charge is that, we also know the charge of the proton is the same as the charge of the electron. So E is going to be Q over K, Q over R squared times K, if we assume they are in a vacuum. A Van de Graaff generator has a dome of radius 15 centimeters. The dome carries a charge of 2.5 times 10 power negative 6 coulombs. It can be assumed that the charge acts as if it were all concentrated at the center of the spherical dome. Calculate the electric field strength at the dome's surface. That is simple. E is equal to K Q over R squared. R is given because we are finding at the surface. R is given, the charge is given, we just substitute. So you should be able to attempt that self-check. That is the end of lesson 2. We are only remaining with one lesson, that is lesson 4, before we move to past paper questions. Thank you for watching this lesson. Have a good time. Bye bye.